Hi all. We're going to have Dr. Tina Mazaheri presenting in a minute, but we'll just give people another couple of minutes just to make sure.
Hello, everyone. Thank you for joining. My name is Tina, and today I'm going to talk about electrophoresis. Just to highlight that the main focus of this talk is the analytical aspects of electrophoresis rather than its clinical implications, because I think that's the main idea behind these lectures, to make us more familiar with the analytical aspects of methods. Okay, right. So I'm going to cover the following topics. First, I start with principles of electrophoresis and the types of electrophoresis. Talking about factors that affecting electrophoresis, different components of electrophoresis, but also the technical consideration, especially in gel electrophoresis, that's important to know. I also briefly talk about lipoprotein electrophoresis and capillary electrophoresis, and then I will give few clinical cases as an example. And then I end my talk with describing principles of immunotyping and when to use immunofixation. Okay, so what is electrophoresis? So we know it is simply the movement of charged particles under the influence of electric field. And we have two types of electrophoresis. You might see different types in different based on where you're reading it from, but I think it's just the main two categories is one of them is zone electrophoresis, where charged molecules travel in a supporting medium. And the examples of these are gel electrophoresis and isoelectric focusing, for example. And then we also have moving boundary electrophoresis, where charged molecules migrate in a free solution. So an example of this is capillary electrophoresis, and I talk about them in details today. So how does the movement in electrophoresis happen? So what factors drive the electrophoretic mobility? So we have two, so you can see we have two electrodes, one is negative, the other one is positive, then we apply voltage, and then the charged particle moves toward the opposite electrode, right? And when the particle moves through the medium, it's under the influence of two forces. One of them is driving force and the other one is drag force. So driving force is the force that pushes the particle in one direction. And the size of this driving force depends on how strong our electric field is. It also depends on the charge of the particle. So the formula for driving force it equals electric field. So E is for electric field times by Q, which is the net charge of the molecule. So obviously, if we have a strong electric field, or if we have a greater charge of the molecule, then the driving force will be greater and the particle moves faster. But then at the same time, we know that when the particle moves in a medium, there is a resistance towards that particle. For example, in a viscous medium, we know that this drag force slows down the movement of particles through the solution. And the formula for drag force is called Stokes' law. And it is calculated, it's basically calculated, so drag force equals 6 pi times eta. So eta is the viscosity of our fluid, times r, which is the radius of our particle, times v for velocity. And at terminal velocity, the driving force is equal to drag force. So this is the speed at which molecule traveling through the solution is basically determined by the point that driving force balances out the drag force. So when we rearrange, so we said our driving force was E times Q, and then we have the drag force, which is calculated by Stokes' law. And when they're equal to each other, and when we rearrange this formula, then we can see that electrophoretic mobility, or the migration, simply the migration rate or the velocity of our particle, is directly proportional to our electric field and the charge of molecule, and also inversely proportional to the viscosity of the medium and radius of the sample size. This formula might look a bit complex, but it's actually the concept that we are already very familiar with. It basically just says that as our electric field gets stronger, or we have a highly charged particle, then the speed of the particle will move faster. On the other hand, if we have a very viscous medium or a large particle, that will have a negative effect on the speed of the particle. So it's a very familiar concept, but it's worth to remember this formula. Right, so factors affecting the mobility of ions, or just the electrophoretic mobility. So we already talked about the net charge of the molecule, the size, the electric field, and also the viscosity. The other two important factors are, one of them is ionic strength of the buffer that we use in electrophoresis, and also the temperature, which I'm going to talk about more in future slides. Right, components of electrophoresis. So we have support medium in this picture. You can see it's a gel. Then that's where separation of proteins take place. We have buffer, and as you can see, gel must be fully saturated by the buffer. We also have positive and negative electrodes on either side of the gel, and then the power supply to provide the electric field. And then we apply the samples in a sample well. And so I'm going to talk about each of these components in more details. Let's first start with power supply. So power supply provides electric fields and controls the current. And this is described by Ohm's law. So just as a reminder, so E, that's our electric field strength in volts or voltage, or electric field strength generally, equals the current times resistance. So basically what Ohm's law says is that the higher the voltage, the higher the current. And when we have a higher current, we have a faster migration. One example of this is, for example, in capillary electrophoresis, the voltage that is used is actually very high, and that gives us a very good and fast turnaround time, unlike gel electrophoresis. So using high voltage will improve the current and will improve your turnaround time. But when you have current flowing through medium, we know that that current faces resistance, and this resistance generates heat. And this heat is actually, this heat that is produced, it causes all sorts of problems, but it can be calculated by the voltage that is applied times the current in a specific time. So just a quick summary. So with higher voltage, we have the current increases, therefore the migration increases progressively. But then when current increases, we have higher resistance and more heat generates, which then affects migration. And then you can see the Joule's law, which I put it in a green box. Basically, the heat that is produced is calculated by Joule's law. And it's basically just a combination of these two formulas, the Ohm's law and the other one, which I just mentioned, that the heat that is produced, it's basically, Joule's law says that the heat is directly proportional to the square of the current and also the resistance. So, in summary, when we apply higher voltage, that will give you a sharper band separation. But the problem is with higher voltage and higher current, we have the heat effect, which this heat, because heat in general can cause denaturation of proteins and degradation, it also affects the protein migration. It's not good at all. So that's why it's really important in electrophoresis that we strictly control the temperature. And that's why we use cooling system. And there are different types. There are different types of cooling system. For example, in capillary electrophoresis, we use Peltier device, which transfers the heat from one side to the other side using electrical energy. So temperature really important to control in electrophoresis. Okay, the other component of electrophoresis is buffer. So basically, buffer carries the current, but it also controls the pH. And when we are choosing a buffer, it's really important to choose a buffer with optimum ionic strength. I will tell you why. Because when you have a stronger buffer, you will end up having better band separation, better resolution, which is good. But at the same time, with stronger buffer, again, your current increases, resistance increases, and that causes the heat again to be generated. And we already said that heat is causing issues in electrophoresis. On the other hand, if we use the low ionic strength buffer, weak buffer, then that also reduces resolution. So because your current that's passing through that medium is overall reduced. So it's really important to find a balance. So in summary, high ionic strength improves the separation of proteins, but it's really important to reduce the temperature. So again, talking about cooling system. So this is the second time you're talking about temperature control, one when applying high voltage, and now with buffer with high strength. There's also, you can also add molecules to the buffer to influence migration, to get better resolution, basically. And one of these molecules is SDS, and it's a detergent that unfolds protein, and it disrupts any non-covalent interaction. Basically, what it does is that it removes the impact of the charge of the protein. So the proteins are separated only based on their molecular weight, and that helps with higher resolution. You might have seen when you see different types of electrophoresis, you might have seen SDS, polyacrylamide gel. So SDS is basically just when you use SDS, you have a higher resolution electrophoresis because the proteins are just separated based on their molecular weight. The other component of electrophoresis is obviously gel. So your support medium or matrix, and that's where protein separation takes place. And I talk about 3 different types of gel electrophoresis in this lecture today. So one of them is cellulose acetate. It is cheap, but it needs lots of the process of preparing it and running it is quite time consuming and labor intensive. And my understanding is that it's kind of like it used to be in the past, it was used more often, whereas now it's largely been replaced by agarose gel. And the agarose gel, which is the one that we commonly use in the lab, the pore sizes in agarose gel is very large. So it is good for example, large fragments of DNA. You might also say that it's actually the pores are large enough for all proteins to pass through. And so the separation is basically based on charge to mass ratio of the protein rather than the weight, because everything was just passed through. It's got several advantages. It's quite cheap. It's non-toxic. It has low affinity for proteins, and it's got a very good clarity. So once the electrophoresis is run and you put it in densitometry, it gives you very good results. And then there is an issue with gel electrophoresis. One of the issues is electroendosmosis flow, which I talk about it in the future slides. But basically, there are some low quality agarose gels that they have very high sulfate, and that causes electroendosmosis problem issue, which affects the resolution of the bands. But actually, fortunately, we have with purification methods recently, it's not recent actually, but there are some purification methods that enable us to prevent this electroendosmosis flow, so that which in turn improves the resolution. So basically what I'm trying to say is that it used to be a problem, electroendosmosis flow, especially with low quality agarose gel, but fortunately that's not a problem anymore. Okay, and then the next gel is polyacrylamide gel. So it is a very strong gel. It's relatively chemically inert, which is a good thing. It has uniform pore sizes and actually can be made in a wide range of pore sizes. And the separation is based on both charge to mass ratio and also the molecular size, because the pore sizes can be smaller. And then, for example, it's really good for shorter fragments of DNA. You also see a very good separation, and it is uncharged. So electroendosmosis is not a problem here. So as I said, I will talk about it a bit more in detail. The only issue with it is that it's neurotoxic, so it's really important to handle it with caution. So I made this table because actually in my exam, part 1, it was one of the questions, differences between agarose gel and polyacrylamide, and I didn't know the answer. So I thought to just put this table. It's basically what I already talked about, but just to make it a bit, hopefully a bit more clear to understand and remember. Right, so the other component in electrophoresis is obviously the detection system. There are several ways to detect the results after you run the electrophoresis. So you can use UV or visible spectrophotometry. An example of this is the capillary electrophoresis, where we use UV spectrophotometry. And it looks at peptide binds absorption at 220 nanometer, which is a UV range. We can also use staining, so different dyes are used. Sea Brilliant Blue, apologies if I'm not pronouncing it correctly, but is commonly used in commercial serum protein electrophoresis. Silver nitrate is another dye that is used, and it's got a great sensitivity in staining proteins. The other detection system is fluorescence or chemiluminescence. And the last step is quantification, obviously, to quantifying these proteins that are separated. So we can do this by using densitometer. And in the densitometer, a laser beam is passed through the sample, and the absorbance of each fraction, the specific wavelength, is measured as it scans through the sample. And then it's basically the intensity of each pixel is proportional to the amount of absorbance of the laser beam. And then it displays as an electropherogram. And then the software measures area under the peak. And when we put the number of total protein, how much total protein is our serum, we put that to the software, and then the software measures the area under the peak and reports it as a percentage of total protein. So we can have a relative concentration of that separated protein. There are some technical considerations in gel electrophoresis, which is important to remember. Once you run the electrophoresis, you might see some issues. You might see some discontinuities in bands, for example. This can be caused by different reasons. It might be because of dirty applicators, air bubbles. So it's really important that when you're running electrophoresis, always check the pipette tip before applying the sample, because any air bubble can cause us problems in the quality of bands. You might also see unequal migration rate across the gel. Again, this can be due to dirty or faulty electrodes, which can cause uneven electric field. It might be because of the uneven wetting of the gel. So we said gel must be fully saturated with the buffer. Otherwise, it can cause problems. And then sometimes air bubbles can be trapped in the gel, which affects the band. The storage of gel is also important. So if you store the gel very close to the heat source, then it can basically dry it out unevenly. And also gels must be kept horizontal during storage to just avoid any uneven thickness. And sometimes you might see washout areas, which can be due to excessively wet agarose gel or when your sample is not concentrated enough, like the urine sample or CSF sample. Right, so electroendosmotic flow, electroendosmotic flow, which I talked about earlier, basically it's mainly a problem with low quality agarose gel. And what it is that basically when you have a low quality agarose gels, they contain sulfate and carboxyl groups. And sulfate and carboxyl groups, they become ionized and negatively charged in basic and neutral buffer. And because these groups are fixed to the gels, they cannot move, right? But their counter ions, which is H3O+, that move towards cathodes. So basically, this causes the flow of water towards the cathode, which affects protein migration. And I said that thankfully with the use of ultra-pure agarose gel, which has very low sulfate and carboxyl content, this basically we have prevented this problem. The other issue with gel electrophoresis is weak flow. And what is weak flow? It's basically during electrophoresis, the passage of current through medium with resistance basically generates heat. And this heat causes evaporation from the gel. And this drying effect causes buffer to move into the support medium. And if it is significant enough, then the flow of water can also, buffer can affect protein migration by causing uneven movement and reducing the resolution of separation bands. Right? So basically, just the flow of buffer in supporting medium due to evaporation of moisture from the gel because of the heat that is generated. How can we minimize this? Again, temperature control is really important. So we talked about temperature control when we used high voltage, when we used buffers with high ionic strength, and now also for weak flow. All of these are the causes that is really important that we have a strict temperature control during electrophoresis. Proper gel preparation also is important. So the gel consistency should be even. It should have an appropriate thickness. And also buffer conditions should be optimized to help to prevent weak flow. Right, so an example of gel electrophoresis, I thought to show you a lipoprotein electrophoresis, which you can use actually you can use acetate cellulose gel, but also agarose gel. And well, we used to use it a lot, not anymore. It's rarely used these days, and we know that it's not used in many labs. So it's a send-away test that is done by a few labs. And one of the indications of requesting lipoprotein electrophoresis is when we are suspecting lipoprotein X. What is lipoprotein X? It's a biliary lipoprotein, and it overflows into plasma in biliary obstruction. It's important to remember it has similar density to LDL, but it does not have ApoB100, and that's why it's not atherogenic. But it causes other problems, especially at very high concentration. So one of the ways when you're suspecting lipoprotein X, you can ask for a serum lipoprotein electrophoresis. So let's first talk about the normal lipoprotein electrophoresis, which you can see in this picture. So you apply the serum sample on the cathode end, right, and the negative electrode. And then we said proteins are separated based on their charge and their size. And there are also proteins are negatively charged in the basic environment. So basically they move towards anode. And on the right side, I just, as a reminder, just put different lipoproteins, which I'm sure you're all very familiar with. So next to the origin, we have chylomicrons. Because chylomicrons are the biggest in size in the lipoprotein, it just stays near the origin point. Sorry, it's not showing in this normal lipoprotein electrophoresis, but if you see the origin, just above the origin, it usually sits very close to the origin if you've got lots of chylomicrons. After that, then you have the beta lipoprotein band. That is your LDL. And then above that, you have pre-beta lipoprotein band, which is your VLDL. So as you know, VLDL is larger than LDL. So you might think that it should actually appear below LDL rather than above it. But the reason of that is because it has more charge. So although it is larger, VLDL has more apolipoprotein in the surface. We know it's got ApoE, ApoC, as well as ApoB100, whereas so overall, it has more negative charge compared to LDL, which only has ApoB100. And then we have the HDL on top, alpha lipoprotein, which is the smallest and moves fastest towards anode. So if you look at the left side, if you see if you're suspecting lipoprotein X, you see a band just below the origin. So it's really important, and I think it has come up in FRC path exams a couple of times at least, that the lipoprotein X, unlike other lipoproteins, it actually moves towards the cathode rather than anode. So you can actually see it below the origin. So if you see a band, if they give you electrophoresis, and if you see a band behind the origin, so in the cathodic side, that can be consistent with lipoprotein X. Just going to check the time quickly. Okay, so lipoprotein. So the next topic I'm going to talk about briefly is isoelectric focusing. And before talking about isoelectric focusing, I just put this slide just to remind ourselves about the structure of amino acids. So we know amino acids, they have amino group, which is a proton acceptor. So when it receives a proton and becomes positive. And also amino acids, they also have a carboxyl group, which is a protein donor, and making it negative when it gives away protein. In a low pH environment, so acidic environment, we know there is a lot of free floating protein. So that means amino group can easily get one proton and become positive. On the other hand, in high pH environment, there's lots of hydroxide groups. So that means carboxyl group can easily give a protein away and become negative. So that means at low pH, amino acid is positive, and at high pH, it becomes negatively charged. So based on that, then we can talk about isoelectric focusing, because the separation in isoelectric focusing is based on isoelectric point. What is isoelectric point? It's the pH at which the molecule does not have any electrical charge. So it's really important in isoelectric focusing that you establish a pH gradient. And as I mentioned in previous slides, proteins have varying numbers of acidic and basic residues. And as the pH of environment changes, the net charge of the protein changes, and they move until they reach their isoelectric point. And that's how they get separated. And you can use it in it has got different clinical applications. For example, for detection of hemoglobinopathy, also in alpha-1 antitrypsin phenotyping, when you have a alpha-1 antitrypsin deficiency, but also for protein isoenzymes, you can use this. The advantages of isoelectric focusing is that it has got high resolution, so you can see sharp and well-defined bands. It's got minimal sample preparation, and as I said, it's got a broad range of clinical application. But there are some limitations with it, which are very actually similar to the limitations of gel electrophoresis. For example, we need to be careful about the gel composition, ampholyte concentration. So ampholites are the charged molecules that establish this pH gradient in IEF. We need to be careful about the buffer systems, the electric field strength. All of these should be very carefully optimized to make sure that we get a good separation. One of the other limitations of IEF, which is this one is specific to IEF, is that because you need to have you have a specific pH range in IEF, then in proteins that have their isoelectric points is above that pH range, then they cannot be separated properly. And then gel artifacts and band distortion. So again, that is very similar with gel electrophoresis as well, that you might see artifacts. And it can be due to lots of factors. It can be due to sample overload, gel imperfections. Again, this applies to all gel electrophoresis, to be honest, but also variations in pH gradient, which is specific for IEF. And it's also they're very sensitive to sample quality. So it's important to be free from contaminants and sample degradation also. So the fresh sample is recommended. Okay, so now let's talk about capillaries. So so far we talked about gel electrophoresis, we talked about isoelectric focusing, and now capillary electrophoresis. Okay. So I'm just going to start talking about electroosmotic flow. So you remember electroendosmotic flow, which I talked about earlier. And I said that's one of the issues with gel electrophoresis. But actually in capillary electrophoresis, we use this principle in our advantage. So basically in capillary electrophoresis, instead of gel, we have this silica capillary. And there are cyanol groups on the surface of silica capillary which are pH dependent, and in high pH they become negatively charged. So just look at the picture on the left side. So the negatively charged capillary surface attracts positively charged cations from buffer solution. So our capillary is filled with buffer, and these negatively charged cyanol groups on the capillary surface, they attract these positive particles, the cations from the buffer solution. And they form the fixed layer of absorbed cations. And then above this fixed layer, you have a diffuse layer. That's where the cation concentration is higher than anion concentration, because these negatively charged capillary can attract more cations from the buffer solutions. And then above the diffuse layer in the center of capillary, then you have bulk solution. And that's where the cation concentration is same as anion. So in the right picture, you see when we apply voltage, what happens? The cations in the diffuse layer attract to the cathode end, to the opposite electrode. And what they do is that they drag the bulk solution with them. And that is called electroosmotic flow. So basically, electroendosmotic flow is the movement of the buffer through the silica capillary as a result of potential difference between buffer and capillary. And that's the principle that is used in capillary electrophoresis. So on top right, you see that's how capillary electrophoresis look like. And then you see below that, that's how the basically inside the capillary. So you have the proteins that migrate through the silica capillary, and they are under the influence of two forces that they are opposite each other. The electroendosmotic force, which I just talked about, and also the electric field, which we know about because we use it in electrophoresis. But it's important to know that this EOF, this endosmotic force, is much stronger than our electric field. And because of that, all the proteins carry towards the cathode end of capillary. And that's the difference between gel electrophoresis and capillary, one of the differences between gel electrophoresis and capillary electrophoresis. Because if you remember, we put a sample and then towards the negative electrode, and then they usually in a gel electrophoresis, and then they move towards the positive electrode, whereas this in capillary electrophoresis is opposite. Because we have a stronger electroendosmotic force, they carry from anode side, positive side, to negative side. So that's why, as you can see, the albumin is, when you see the electropherogram inside this capillary, is different to the gel. The direction is different, and that's why we flip the picture of capillary electrophoresis so it looks similar to the gel. Okay. So basically that's how it looks. I already talked about them. You can see the picture on the below right, you can see 8 capillaries. So that's how the silica capillary look like. And you can basically run 8 samples at the same time. And it's got a very fast turnaround time. If you remember, I said earlier in the lecture that for capillary electrophoresis, we use very high voltage, and that helps us with very fast turnaround time. So actually, with capillary electrophoresis, we can write 80 samples in an hour, which is much faster than gel electrophoresis. And we talked about inside the capillary. So on top, you can see, on top right picture, you can see that the sample is diluted with buffer, and then it enters the capillary from the anodic end of the capillary. And then we apply very high voltage, and the separation happens. And then you can see the detection, and then there is the detection of the protein, which is made at 200 nanometer, or I've seen 220 as well. I'm not sure which one, maybe it's the range. But basically, that's where it's detected by a UV spectroscopy. And then we put the total protein result into the computer, the software, and that helps us, again, similar to densitometry that I talked about in gel electrophoresis. So you put the total protein result into the software, and based on that, the software can quantify the relative protein fractions. So it basically calculates the fraction, the percentage, and then multiply it by our total protein to give us the concentration of that protein. Right, and that's what an electropherogram looks like. So capillary electrophoresis, so that's what it generates. And we know that capillary electrophoresis, we commonly use it to detect paraproteins. But as you can see, plasma proteins are classified into 6 groups. And this is based on their electrophoretic mobility. And that's what the normal protein electrophoresis look like. So first, we have albumin, which obviously is the most abundant protein. And then in alpha-1 globulin region, we have alpha-1 antitrypsin. And it's important to look at this alpha-1 region, because I remember the clinical scientist told me once that they have actually picked up incidentally patients with alpha-1 antitrypsin deficiency. So when you see in alpha-1, you see that there is no peak and it is flat. then that you can suspect alpha-1 antitrypsin. So it's important to look at alpha-1. And then in alpha-2 region, we've got haptoglobin and alpha-2 microglobulin. In beta-1 region, we've got hemopexin, transferrin, C4. Ceruloplasmin can be seen both in alpha-2 region and beta-1 region. And in beta-2, we see C3 complements, beta-2 microglobulin, but also that's where CRP is as well. And then the gamma region is, as I said, we commonly request capillary electrophoresis when we are suspecting if there is any paraprotein. So that is you can see it's a very wide band, it's a wide peak, and that's because we have different immunoglobulins with slightly different sizes and charges. So you see this polyclonal IgG, IgA, IgM, but then IgD and IgE, they are very, very smaller amounts. That all of these, they form this gamma region. Two things that are important when we are requesting about the sample, when we are requesting capillary electrophoresis. One of them is that we know serum is necessary, because if you use plasma, so when you use serum during clotting, the fibrinogen is removed. Whereas if you use plasma, then you have a fibrinogen in your sample, and that causes a peak in beta-2 region, which can cause confusion. It may mimic paraprotein. So really important for the sample to be serum. Also, hemolyzed samples can cause some increased peaks in beta region, and that's where the free hemoglobin migrates. Or because when you have free hemoglobin floating around, then haptoglobin will bond to it, and the hemoglobin and haptoglobin complex can cause an increase in alpha-2 region, or sometimes you might see an extra unusual band between alpha-2 and beta region. So again, good quality sample is very important to avoid any confusion. I'm not going to talk about all of these, but I think it's a good table. I just put it here because it basically shows how different conditions can affect different peaks and different regions in protein electrophoresis. So please have a look of all of this. I think this is a very useful table. And I have included some examples of this at the end of this talk. Right, what is serum immunotyping by immunosubtraction? So when we see this sharp peak in gamma region, that's when it is scary. It represents a paraprotein. Then the next step is to immunotype and identify the type of this paraprotein. So in immunotyping, basically serum is mixed with antisera against IgG, IgA, IgM, kappa, and lambda. And immunoglobulins, if they are present in the serum, they react with this corresponding antisera. And the antibody paraprotein complex is subtracted, removed from the trace. So this disappearance or subtraction in the capillary electrophoresis indicates that there is a monoclonal band present, monoclonal protein present. So exactly where the subtraction occurs, that's where there are monoclonal protein present. So as an example, so in the picture on the right, you can see when the antisera against IgG is added, you see the red peak disappears. So this disappearance, which is the subtraction, of your of the immunoglobulin against antisera, that indicates the presence of our protein. And then again, you see in IgA, the red peak in gamma region is present, so that's okay. In IgM, again, red peak is present. But then in kappa, again, it disappears again. But then in lambda, you see the red peak. So basically, wherever the subtraction happens, that is highlighted with blue arrow on top of gamma region, that means that is the type of our paraprotein. So in this example, our paraprotein is IgG kappa. So whatever that is subtracted with our antiserum. And sometimes you want to do immunotyping by immunofixation gel principle. And I will tell you when this is indicated in the next slide. But in immunofixation, it's basically running a gel electrophoresis. So you run patient's serum in 6 parallel lines, okay? So if you look at the photo, the first one is the patient's electrophoresis, serum electrophoresis result. On top, you see the albumin, which is very, very purple. And then on the below, you see again another strong band, which is in the gamma region. Sorry, maybe I should have just put the regions, but on top is albumin, then you have alpha 1, alpha 2, beta 1, beta 2, and then at the end, top end, in the bottom end of your electrophoresis, you see another very purple band, which is in your gamma region, and that represents the paraprotein, the monoclonal band. So now you want to know the type of this. Then in lane 2 to 4, you basically add antibodies to the serum of the patients against IgG, IgA, and IgM. And then the last 2 lanes, basically antibodies to kappa and lambda light chains are added. And basically these antiserum, they precipitate any antibodies that are present. So you can see in this gel that the antibody paraprotein complex is formed at IgM and lambda. So that's what our paraprotein is, IgM lambda. And when do we use? So when is it that you think that capillary electrophoresis might have some limitations, and when would you consider immunofixation with gel? Because we know that how capillary electrophoresis is very fast, it's automated. Gel immunofixation, more labor intensive, a bit slower. So there are some indications for when to use immunofixation. One of them is that we need to know that capillary electrophoresis is less sensitive than immunofixation. So if you have a very small paraprotein, that might be missed in capillary electrophoresis. It also does not really pick up light chain myeloma. So we've got 3 light chains in serum that we can measure for that. But obviously with immunofixation, you can also pick up light chain myeloma. Also in immunotyping that is done by capillary electrophoresis, IgD or IgE is not used because they are very rare. Whereas when you do immunofixation, you can also add antibodies against IgD and IgE to identify these rare types of paraprotein. There is also interference. So contrast can interfere with capillary electrophoresis, but not with immunofixation. So I'm just going to end the talk with a few clinical cases. So 87-year-old gentleman presents to GP, back pain, anemia, renal impairment. I made it really clear of what we are suspecting here, but also hyponatremia with sodium of 122. So GP requested serum protein electrophoresis, and you can see there is the band, there's a monoclonal band, quite a raised sharp peak in the gamma region. And the highlighted band was quantified as 10.2 gram per liter. Please write an interpretive report for these results. So writing an interpretive report for the results usually comes in part 2, module 1. They also gave us the immunotyping. So we'll give you a few seconds to just look at them. So the first one is your patient serum electrophoresis, the basic sample, and the initial sample, and after that you added antiserum of IgG, and then you see whether the red peak is disappeared in the gamma region or not, which looks like it is disappeared. Then you look at IgA, has not disappeared. IgM, you still see the red peak in the gamma region. And also in kappa, you can still see the red peak in the gamma region, but in L, again, the red peak has disappeared. Just give you a couple of seconds to think about it, the type of paraprotein. So I hope you all agree that it is IgG lambda paraprotein. Obviously, when you see these results like this, especially, well, the first time, if it's a known myeloma patient and if it's coming down, that's not a problem, but results should be found out in the first results. And we said that it is IgG lambda, urgent referral to hematology is important. And then the additional test for myeloma, which I'm sure you're already familiar with, just to highlight that low sodium can also be due to pseudohyponatremia because of the presence of paraprotein and what we see in indirect ISC in the lab. So it's good to think about pseudohyponatremia in the context of paraprotein. And then just a few examples of serum protein electrophoresis. These are the examples that Daniel, one of the clinical scientists who used to work at Imperial and at protein section, he kindly shared the slides with me. But basically, these are the protein electrophoresis. I'll give you a few seconds to look at it and see if you can suspect anything. So you've got your albumin, alpha 1, alpha 2, beta 1, beta 2, and gamma region. But I know that we are running out of time, so I just quickly go through them. You see the alpha 1 is flat. So that is suspecting alpha 1 antitrypsin deficiency. But the rest look okay. That one, I'm going to give you a few seconds to look at them. So looking albumin. Actually, on the left side, you can also see the concentration. And the arrows are also helpful. So basically, this shows there is an increase in what we call it beta gamma bridge. So you can see an increase in beta 2 and gamma region. It's not this increase in gamma region, it doesn't look like monoclonal band, isn't it? It's very wide. It's not sharp peaked. It's not sharp peak, it's quite wide. And you can see this, it is also associated with increase in beta 2 band. And that's what you see in chronic liver disease and cirrhosis. So we know that in liver disease, chronic liver disease, and especially cirrhosis, your albumin goes down. So that's one clue. Your alpha 1 and alpha 2 will also reduce, although it's not very obvious in this photo, but this is because of hepatocellular insufficiency. But then the main thing is beta 2 and gamma bridge. This is because of the polyclonal increase of IgA that you see in chronic liver disease. You can see this pattern. Right, this one. So again, you can see the arrows are kind of giving it away, but the albumin is low. Not really, it's 35 grams per liter, but if we say it is the normal range is 40, then it's slightly on lower side. Alpha 1 and alpha 2 are increased. Same with beta 2 and gamma. But again, with gamma region, there is no monoclonal band, there is no sharp peak, it's quite wide. So it's not paraprotein-like. And that's what you see in the basically in the inflammation. So you see a polyclonal increase in gamma region, which is typical of inflammation. But obviously the proteins that we have in alpha 1 and alpha 2, like alpha 1 antitrypsin, they are, or ceruloplasmin, for example, these are acute phase proteins, right? So they go up in chronic inflammation. And beta 2 is the complement, so that will also increase. Right, I think this is the last one. Give you a few seconds. But here we see albumin is reduced. It's quite significantly. So the albumin is 18 or 19, 18.8. And then we see a massive increase in alpha-2. But then we see the gamma region is quite suppressed. And that's what you see in nephrotic syndrome. Basically, your albumin is significantly decreased. And then alpha-2, you see an increase in alpha-2 microglobulin, and that's because it's a compensation mechanism, basically. Because we have decreased albumin, you have decreased oncotic pressure due to loss of low molecular weight albumin. So then alpha-2 globulin will increase. And that was the end of the example. So basically the reference I used was teats, but teats is quite difficult to read, and it is a bit dry. But it is really good to just always have a look at it, definitely. But I remember when I was preparing for my FRC path, especially because we didn't have any formal teaching back then for analytical method, I was quite lost reading teats. So I used YouTube. Which some of them are quite helpful. Also, William Marsh, I'm sure you're all very familiar with, really good book, but it's mainly clinical applications rather than analytical method. Also use my FRC path revision notes, which for this lecture. And just wanted to thank Daniel and Becky. They were both brilliant clinical scientists who gave their I used some of their slides and examples for this lecture from them. And I think it's really important to, when you're getting ready for the exam, just go through what I did is that, you know, ADLM, or formerly it's AACC, is the American Association of Clinical Chemistry, and they have free online courses. And I found them really helpful. It's just because it's American, you might see like some differences. But actually it's really helpful for looking at different protein electrophoresis. Obviously look out for LabMed UK days and FRC Pathmark days. They are also very useful, and they give you lecture notes again about protein electrophoresis. There are, following these topics, I had no time because, as you could see, there were lots of content that I had to talk about today. So I couldn't cover them today, but it's really important. So please have a look and make sure that you know you're very familiar with ALP isoenzymes, how to interpret them, CK isoenzymes, oligoclonal bands, very important, and also beta-2 transferrin gel and alpha-1 antitrypsin phenotyping. Thank you very much for listening.